Okay, so now we're going to do an example with that velocity concept we talked about at the end of the previous video. And once again, we're looking at a table of values here. So we're thinking of a particle moving along a horizontal number line like the one we gave previously. And its position at various different times are recorded in this table. So we're kind of doing the same couple of things that we did in the previous example, is just with the context of velocity. First thing I want to do is compute the average velocity of the particle over these intervals. Okay, so again, velocity is the rate of change in position over the rate of change in time. So what this means is that on the first interval we want to look at, 5, 10, the rate of change in my position is given by s of 10 minus s of 5. Remember, s is that position function. So this would represent the position at time 10, position at time 5, and their difference gives me the total change in that position over that interval of time. We then divide this by our change in time, 10 minutes, or 10 seconds minus 5 seconds, okay? Now, for s of 10 and s of 5, I need to find that information in the table. So s of 10, at 10 minutes, we're at position 22. So that would be 22. And at 5 minutes, we're at position 5. So minus 5 right there, over 10 minus 5. Now, this is easy to compute either by hand or in a calculator. This comes out to 3.4. Okay? Now, let's do the same thing, but on the interval 10, 15, okay? We're doing the same thing. This time, s of 15 minus s of 10, that would be the rate of change in our, the total change in our position over that interval of time, over 15 minus 10. And looking to the table for that information, s of 15 is equal to negative 4. S of 10 is equal to 22 over 15 minus 10. And this one comes out to negative 5.2. Both of these have units of measure because we're talking about velocity. And we use the units that are given to us in the problem to determine what the rate of change, the units of the rate of change. So it's going to be meters per second. Meters per second. Okay, now notice here I've computed two average velocities. One of them came out positive and one of them came out negative. And think about what that means, okay? So in the positive case, if we look at our number line, over this interval of time here from 5 to 10, where did our particle go? Well, at 5 seconds, we were at position 5. And at 10 seconds, we were at position 22. So we moved from here to here. Okay? I'm using the convention that the numbers get larger as they move to the right and smaller as they move to the left here. Now let's look at this case. What happened as we moved from 10 seconds to 15 seconds? Well, our particle moved from the position negative 4, from the position 22 to the position negative 4. It started here, and then it moved here. So what we're seeing, if we try to correlate these quantities to these depictions of the movement of our particle, we're seeing that a positive velocity means that we're moving towards the right. Again, under the convention that moving to the right gives you bigger positions, bigger numbers. Moving to the left gives you smaller numbers. If you have a negative velocity, then that means that our particle is moving to the left. And that's what we're seeing here. So that's how we make sense of the positive and negative velocities. One means to the right, the other one means to the left. Whoops. All right. Part B is saying approximate V of 10 using the results of part A. And using the same reasoning as the last example, because of the intervals that we used here, 5 to 10 and 10 to 15, 10 is right in between. 5 and 15. It's right there. It's kind of the midpoint of the interval if we put these two together. And so we can approximate v of 10 by taking the average once again of these two slopes, these two velocities. 3.4 plus negative 5.2 divided by 2. This works out to negative 0.9 meters per second. So what does this tell us? Well, if this approximation is a good one, it's telling us that we are moving towards the left after 10 seconds. And it also tells us that we're moving at a speed that is less than the speeds here. Now, I'm using the word speed instead of velocity. What do I mean by speed? Well, the speed of a moving object is just the absolute value of its velocity. In other words, it's the same thing as velocity if we take away the negative, if one exists. Okay, so the absolute value of this would be 0.9, which is less than the absolute value of either of these. But this indicates that it's moving to the left. Now, can we be certain that the object or this particle is moving to the left after 10 seconds? And no, we can't be certain because, again, this is only an approximation. And we're pretty close to 0 here. If we're off by enough, it's possible that the velocity at 10 is actually a positive number. But usually, this approximation gives us a fairly reliable result. Okay, so I already talked a little bit about this, where we said that a particle is positive when it's moving towards the right, negative when it's moving to the left. What we have not encountered yet is what it means if a velocity is equal to 0. Well, if it's equal to 0, then it's neither positive nor negative. So that means that the particle is not moving to the right and it's not moving to the left. And because those are the only two directions this particle is allowed to travel, that must mean that the particle is not moving at all. We can understand this. Using the formula for velocity as well. If velocity is equal to 0, then by definition, delta S over delta T equals 0. Remember, that's how we define velocity. But this is only true if delta S equals 0, which means delta S equals 0. And let's think about what that means for a second. Time has passed, but our position has not changed because we have moved 0 units. Now, in reality, that does not mean that we haven't moved at all. That just means that our starting position and our ending position are the same. It's possible that as time passed, our particle moved and then turned around and came right back to where it started. In that case, our starting position minus our ending position minus our starting position would be 0. But this is how we want to think of as 0 velocity. We want to think of it as the particle having not moved at all, or it's at rest. That's the term that we'll use a lot. Okay. One more example before we wrap things up. This example is from your book, and we're doing essentially the same thing, but this time instead of working with a table of values, we have an actual function. And this is an important function to know. So the function that we're using models free fall. If you hold an object at rest and then release it, you just drop it without propelling it downwards. So you're not giving it any initial velocity. You're just letting it go. Then we can model the rate of change, we can model the amount of distance that object would have dropped by taking gravity into account in doing experimental observations. And even before we had a workable theory of gravitation, we were able to observe positions of a falling object and come up with this position function. So in this case, if we think of our number line once again as oriented this way, where 0 represents the object's starting point, and then we let our units become larger as we move downward like this, then the object will fall in the positive direction. Okay, and so that means that the position of this object will only ever be positive because we're not throwing it upwards where the negative numbers live. But this function, s of t equals 4.9 t squared meters is the function that gives us the position along this number line of a falling object after t seconds have passed, okay? Now, it's important to also note that in physics, we have a lot more to consider. This is the function that would work for free fall in a vacuum, meaning we have no air resistance to oppose the motion of that, the downward motion of that object. So when air resistance is taken into consideration, this gets more complicated. To keep things simple, we're not going to consider air resistance. So let's assume that an object has been dropped from a very tall tower, and after 5 seconds, the object is still falling, okay? What I want to do is approximate the instantaneous velocity of that object 5 seconds after being released. And you notice I have a table of data that we would have had to compute in a calculator. But I'm going to show you where this is coming from. So for example, on that time interval from 5 to 5.1, we can compute our average velocity over that interval using this once again. S of, oops, not t, S of 5.1 minus S of 5 over 5.1 minus 5, okay? Now this is equal to what I would get from plugging 5.1 into this function. So 4.9 5.1 squared minus, and then again here I would have 4.9 times 5 squared. 5.1 minus 5 is equal to 0.1. And I could plug that into a calculator. I think this one comes out exact, actually. We get 49.49 meters per second. That's where this is coming from, okay? And then I would repeat this process, because remember, when we were trying to approximate the slope of a tangent line, which is technically what we're doing here, we wanted to collect a lot of data using points that are getting closer and closer to that point where we're finding our tangent line at. In this case, the point where t is equal to 5. Graphically, we get something that looks like this. So the curve, the black curve that we see here, is the graph of the parabola s equals 4.9t squared. Since time is going to be measured using non-negative quantities, there's not going to be a left branch of this parabola that we can use. So it's only the positive stuff over here. What we're doing is we're taking a point that's near 5, but greater than it in these cases, and creating an interval out of that. So this right here, that's the interval 5 plus h. Now what is h? Well, h is that change in t. I can think of h as delta t. It's just a different label for it, because that's the amount by which time is changing as we go from 5 to 5 plus h, okay? So that h is going to be showing up down here. It's that change in time. The h that I'm showing here, again, will vary depending on what my right endpoint of each of these intervals are. So in this case, where I go from 5 to 5.1, I've increased 5 by a value of 0.1 to get from here to here. That means h is equal to 0.1 in that case. Here we go from 5 to 5.05. We've increased by 0.05 in that case. So h is equal to 0.05 there, okay? And I'm not going to fill in the rest of that, but what does that tell me? If I wanted to generalize this, if I wanted to find the average velocity on the interval 5 to 5 plus h, then that would be equal to this, s of my right endpoint, again, same thing that we did up here, s of 5.1, s of 5 plus h minus s of 5 over 5 plus h is my right endpoint minus 5, because that would be the change in time. Of course, the 5's here can cancel, so this is equal to s of 5 plus h minus s of 5 all over h. Now this should look somewhat familiar to you. If you go back to the Are You Ready for Calculus videos that we did, we talked about this thing called a difference quotient in one of those examples. And that's what this is. So we're starting to see where that difference quotient idea is popping up. Okay, and we'll do a lot more with that idea as we progress through chapter 2. But with this example, let's see, did we do everything that we were supposed to do? It says an object is dropped from a tall tower. Assuming the object is in free fall and neglecting air resistance, approximate the instantaneous velocity of the object 5 seconds after being released. This is where we look at the trend in these average velocities. Because again, each one of these is actually the slope of a secant line. And we know, based on what we've seen before, that as Q gets closer and closer to P in this graph, then the corresponding secant line is more closely approximating the slope of that tangent line. Or the slope of that secant line will become very close to the slope of that tangent line. These are those slopes. I'm getting pen everywhere. What kind of a trend do we see happening here? 49.49, 49.245, 49.049, 49.0049. What appears to be happening is that as we get better and better approximations, our average velocity is tending towards 49. That's what it looks like, okay? So our guess here is that our velocity, which is what those slopes represent, at the exact instant of 5, the instantaneous velocity, we believe will be 49 meters per second, okay? The data appears to be pointing in this direction. Now, even though that's the only way that we've been dealing with these approximations, we sort of say this is what appears to be happening. We don't know for certain that we have this right. For example, how do I know that the instantaneous velocity is actually not 49.000001 meters per second? Maybe I'm off by a tiny little bit. And in the next few sections here in chapter 2, we're going to show how to evaluate this so that we have absolute certainty that we're doing it correctly by not having to rely just on data like this. But this is as far as we're going to go in this first section, so let's wrap this up here.